A construction crew halts operations. A massive concrete pillar is scheduled to be poured exactly where a prefabricated plumbing main has already been routed. The engineering disciplines have clashed directly on the physical site. Modern architecture, engineering, and construction projects are massively dense structures. When structural engineers, architects, and mechanical contractors design their respective systems in isolated digital silos, spatial conflicts are a mathematical certainty. Finding these conflicts in the field results in thousands of dollars in wasted materials and cascading schedule overruns. To preemptively map and eliminate these physical intersections, the industry utilizes Building Information Modeling Coordination, or BIM. The engine driving this precise digital coordination is Autodesk Navisworks. There is a common misconception about the software. Navisworks is not a primary authoring tool. Unlike AutoCAD or Revit, it is not used to draft the original 3D geometry of a pipe or a steel beam. It is strictly a project review and aggregation environment. Its function is to intake thousands of independent data points and detect the errors between them. Navisworks shifts the entire cost of conflict resolution from expensive physical demolition to inexpensive digital adjustments. This diagram outlines the three-stage pipeline required to reverse engineer a fully coordinated digital twin from scratch. Phase 1 requires merging isolated engineering files into a single comprehensive spatial database. Phase 2 introduces strict spatial constraints, systematically identifying any point where structural systems physically overlap. Phase 3 moves beyond physical geometry by adding time, injecting scheduling data into the structural components. The central tension of any megaproject lies right here. Teams must guarantee that thousands of independent, multidisciplinary elements will perfectly align, both physically and temporally, before a single shovel hits the dirt. Achieving that guarantee means starting with a completely blank digital space and meticulously building up the data layer by layer. Every complex development begins as a fractured dataset. Independent teams generate highly detailed 3D models, specific only to their scope of work. Architects export IFC files, MEP teams use Revit, and structural engineers work in AutoCAD. Navisworks acts as a universal translator, importing these disparate formats and stripping barriers. Through model aggregation, these separate environments collapse into a single unified XYZ coordinate space. The final result is a federated model. It is a holistic, multidisciplinary replica of the entire site, housing every pipe, wall, and wire in one digital ecosystem. Establishing this single source of truth is the absolute prerequisite. No meaningful project analysis can occur until every discipline occupies the exact same digital geography. Moving inside this newly aggregated federated model reveals a visually chaotic environment. It is a dense web of overlapping structural and mechanical systems. Relying on a human reviewer to manually fly through this density and spot every millimeter of error is mathematically impossible. The complex geometry requires automated spatial analysis. This is where the Clash Detective tool engages. It systematically queries the database, isolating exact coordinates where distinct geometries intersect. This table breaks down the ecosystem, showing why executing this spatial analysis requires the correct software tier. Navisworks Simulate and Navisworks Freedom are highly capable for viewing and temporal pacing, but they lack the algorithmic engine. Only Navisworks Manage possesses the automated spatial clash capabilities needed for deep structural analysis. Once the engine flags these hard intersections, the model review phase begins. Coordinators isolate the exact XYZ coordinates of the neon red crashes, annotate the specific components involved, and bundle them into detailed reports. These reports are routed back to the primary authors. The structural engineer opens their native file, shifts the beam or routes the ductwork around the obstacle, and resubmits the clean file to the federated model. Catching that neon red clash inside Navisworks costs a few minutes of digital collaboration. Discovering it on a physical site costs days of idle labor and thousands in wasted steel. Eradicating spatial intersections only solves half of the coordination equation. The materials must also arrive and assemble in the correct chronological order. To achieve this, the workflow introduces 4D construction simulation, taking the clean 3D geometry and injecting the fourth dimension, time. This layout demonstrates the timeliner interface mechanism. It directly links specific 3D model elements on top to exact tasks on the project schedule below. As you scrub through the timeline, the building constructs itself sequentially. Every beam and panel appears precisely according to schedule. 4D simulation exposes logistical bottlenecks. It allows managers to visualize congestion, optimize crane placements, and validate the exact sequence of operations long before heavy machinery arrives on site. This temporal data also drives precise quantification. Estimators can dynamically calculate material costs as the schedule progresses, tracking expenditures against the timeline. Ultimately, 4D coordination provides a risk-free environment to rehearse the entire physical build, mathematically proving that the schedule is viable. Navisworks is a rigorously engineered platform, but it operates under strict environmental limitations. Aggregating tens of millions of polygons demands significant overhead. It requires massive RAM, robust CPU architecture, high-performance graphics cards, and substantial software licensing budgets. It is not an accessible tool for low-capital operations. But the ultimate constraint is the garbage-in, garbage-out data paradigm. Navisworks cannot magically fix bad engineering. If an architect imports an incomplete floor plan, or an engineer uploads inaccurate pipe diameters, the clash detective will yield false positives and fatal omissions. Its output relies entirely on the accuracy of the imported models. Maximizing the software requires high capital investment, paired with highly disciplined data hygiene across every department. As the scale of commercial development continues to grow, the coordination workflows inside Navisworks are evolving to match. AI-assisted algorithms are being deployed to automatically resolve minor geometric clashes, while cloud-based platforms now allow global engineering teams to share and edit federated models in real time. The clear trajectory is the adoption of digital twins, living, data-rich replicas of physical buildings that facility managers use for life cycle management decades after construction ends. Concurrently, augmented and virtual reality integrations allow on-site workers to wear headsets and overlay these 4D simulations directly onto the physical job site. The process moves predictably from isolated data silos through rigorous spatial clash detection, and finally into optimized 4D spatiotemporal simulations. In the hyper-complex architecture and engineering space, robust digital coordination is the definitive barrier. It is the only metric separating a highly profitable delivery from an unmitigated logistical failure.